So can I erase the names? Okay, so it's Friday afternoon, so and I was supposed to talk about D modules, and I plan to say something about D modules, but basically I just want to get some input from you about how much you know of formal algebraic geometry. We need just few basic ideas. And also, I decided not to do any serious calculations today because I would probably get everything wrong. So I will just give you some rough ideas about D modules and how you do D module, how you use D modules in representation theory. One thing you saw in these lectures, I mean, we came long way from Monday when we started with a very simple and clearly defined problem when we discuss representations of finite groups. One of my colleagues here, who is topologist, he always tells me, you guys are algebraists. And I'm always upset about this because if you think what we were talking about this week, we talked something about algebra, but it was a little bit of algebra. We talked about differential equations, which is analysis. We talked about integration. So one hard thing in representation theory that we are mixing techniques all the time and making things look really confusing, but at the end, you usually get some really new insight. And this is what I plan to do today. I just want to confuse you even more, hoping that next week you will see something which you will appreciate. So let me start. I have to copy this because I'm sure I would do horrible things if I try to do this on the spot. Let me look at three differential operators. So I'm looking at complex plane. I could look at it at a line. It's just a real line. It doesn't matter. But in our applications, actually, this will be complex plane. And I'm looking at three differential operators on this. Say E is minus z squared times the derivative with respect to variable z. F is just the derivative with respect to variable z. And H is 2 times z times partial, times derivative. So do you see anything special about these differential operators? What? Yes. Okay. So, I mean, I gave you a hint by labeling EFH. So if you calculate the commutators, and I mean now he told my little secret, so I even won't do the calculation. If you do the calculation, you see what we expect to have. So this is HE is 2E, HF is negative 2F, and commutator of E and F is equal to H. So this is nothing else than the commutation relations from our Lie algebra of SL to, say, C or R, whatever you want. I mean, I'm working over C now, and you will see later why, where, say, H is, say, 1, 0, 0, minus 1. E is 0, 1, 0, 0. And F is 0, 1, 0, 0. So we have these three differential operators which span our Lie algebra of SL2C. So we have a simple geometric method, or if you want, analytic method, model of the Lie algebra of SL2C.
Let me point out, this is very similar to what I wrote down for H
Shut up. It will be exactly the same. So now let's construct a module. Yeah.
I'm not very comfortable with the notation of the AE equals minus C squared differential operator. Would you mind doing one of the examples, just computing one of them?
Oh, I mean, let me calculate this. So let's see which one is the simplest. So H times F. Okay, no, actually, this is a very good question. So to calculate this commutator, I have to calculate this some function f. So what is this? This is h f f minus f h f.
The commutator is just the difference between the two things written.
Yeah, I mean the commutator, if I have differential operators as special cases of linear maps, if you have a commutator of two guys, this is, you take f composed with e and then subtract their composition in opposite order. So now if I want to calculate this, let me do, what did I say, h and f. So this is 2z, and I mean this partial, what I actually want to do is ddz, but partial is easier to write. And I have f is partial applied to, so okay, this is d dz applied to f. I mean, this is just pure calculus, so you shouldn't worry what f is. Just do as our students. This is second derivatives of f minus, now I have to do this in the other order, so this is d dz, 2z, d dz applied to f. Agree? Okay, so this guy is taken care of, but now I will use the product rule to differentiate this. So let me do this. So I have 2z df dz, and then I have minus 2z. Oh, I'm not, this is gone. Yeah, you're right. I told you that I shouldn't be doing this, but, and now second derivative of z. And of course, the whole thing is done in such a way that these two guys cancel out, and we get this, and this is negative 2 df dz, and by our notation, f is just derivative, so this is minus 2f applied to the function f. So now if we compare this, we just get this commutation relation. Okay, good. So we are making progress. Okay, so now let me look at a specific module. Now I will take these differential operators act on functions on a complex plane. And I could look, say, at all polynomials. I mean, Castleman would jump that this is half of his picture. But I want to get more or less whole picture he used. So I will take all rational functions in a complex plane having poles at the origin. So basically, I'm looking at the module V which is linear span of all Zn's and goes over all integers. Is this a module for SL2? For this guy here. Yes. So, because I'm just... So, let's look at the submodules. For example, inside this, I have all polynomials. I have a submodule of all Zn's when n is positive. Yeah.
Something about rational functions with positive origin.
They need not have
Where
poles.
they come?
I mean, they,
The only place there might be a pole.
Yeah. Rational functions having possibly pole at origin. No, I mean, I'm not. Yes. I mean, I'm allowing poles to have order 0. Or, so basically, this span of these guys are polynomials. And if you look, our differential operators have regular coefficients, so definitely polynomials form an invariant subspace. Inside this invariant subspace, there is also invariant subspace of constants. There are also annihilated by all of these differential operators. So the line C, which also sits inside this, is also a subspace. But the space I want to look at in detail is actually the quotient. Let me denote this, say, by V plus. I want to look at V mod V plus. So this is the space which is spanned by z to the minus 1, z to the minus 2, and so on. So I can view this as, say, truncated Laurent series of my, just a second, let me finish the sentence. After the period, you can add. So truncated Laurent series at the origin, and they are also a submodule of a quotient module of V, and they form a module for this Lie algebra SL2C. Yeah, go ahead.
So we do want this to be Laurent series, not necessarily. We want this to be completion of V of this.
Everything is algebraic. These are finite Laurent series. We are dealing with rational functions. What?
they're rational functions, but the denominators are all powers of z.
Yeah, because they're rational. They can have poles only at the origin. Yeah.
Laurent polynomials.
Yeah, Laurent polynomials. Yeah.
But it could go. I mean, the whole
No. I mean, I am not. I will be doing algebraic geometry. We don't want any convergence. No, we had enough of convergence stuff. Everything is really very basic. So these are finite sums. If you want, this is C, Z to the N, and, oh, no, I mean, this is algebraic sum of these guys. Yeah.
Did you get this by making SL2C act on P1C and then differentiating?
Yes. Yes. I mean, this will be the end of the story. So I just want to point out, I mean, if you look at, so this is a module.
I'm sorry. Why is that quotient a G invariant? Or sorry, SL2 invariant?
Do you agree that V plus is G invariant?
Oh wait, never mind. Yes, that's fine.
Oh, I mean, it's a very good question. It's not clear that a priori that's invariant, but the way I constructed it, it's clear, because I took something invariant and I quotient out with something invariant.
Oh, the question was z inverse. When you differentiate it once, then multiply it z squared, you get 0.
Yeah, no, I mean, you have a point, because let's see what kind of module is this. What happens if I claim that this is a module which appeared in first Castleman's lecture, in first Trapa's lecture, and then over and over and over. And this is one, oh yeah, you have to guess what it is in a moment. But let's see what happens when I act with f. If I act with f, I am differentiating negative power of z, so I'm getting bigger negative power. I'm increasing the order of my pole. If I apply h is this guy z partial z, just differentiation increases the order of pole, multiplication by z decreases by 1. So I have the same order of the pole times some number, and I don't care what this number is. And what is E doing? E is pushing the n down by 1, and then I am multiplying by z squared, and I am doing this twice. Now, of course, we are getting to your remark. What happens if I apply E to 1 over z in this quotient module?
You get something in V plus, which gets
Yes. So it's 0. So what kind of module is this? Yes. So this is one of Verma modules which appear before, and the way how we constructed it by basically realizing the Lie algebra as a bunch of differential operators, and then using this realization, we constructed a model for a Verma module, and the theory of D modules allows you to do this in general and to do it in a useful way. So now I will erase this, and I will give you a simple analogy from algebraic geometry. But before that, let me clear up something. So how many of you had any algebraic geometry? And I'm not talking about, say, in how many lines 3 quadrics in who knows what kind of space intersect, but just the formalism that you know what is, say, affine algebraic variety, what are regular functions, and such things. Is this okay? So it seems that most of the people are familiar with this. So if you have any questions, so just ask me or any of us. So let's go into baby algebraic geometry and look at it formally, how geometers study things. I mean, they would probably be disgusted by my version of this, but so first notion, I believe we are going to work over C, because this is what we need in applications. Yeah, I mean, I should probably, this is unnecessary, but because these titles, these lectures are about D modules, and what you saw from this example, D stands for differential operators. But let's look at something much more primitive. So what one does when you study algebraic variety, algebraic varieties, you look at Cn, and then you define, say, affine varieties or sometimes closed algebraic sets. So these are subsets of Cn, so that where Z is just the set of zeros of bunch of polynomials. And P goes, say, Pi, I goes from 1 to some number n. I mean, I can consider whole ideal generated by this and so. So basically, we are studying on Cn. First of all, we can define so-called Zariski topology, which is a topology where the closed sets are zeros of polynomials. And then we define closed algebraic sets as such subsets, and we define Zariski topology as the topology induced by Zariski topology on Cn on this set. So in this way, we get a bunch of weird topological spaces. And then we define regular functions on those spaces. First, I have regular functions on Z is that I define R of Z are all polynomials, say, let me denote C of, say, Cn. These are all polynomials on Cn. And I of Z, these are all polynomials vanishing on Z. So basically, the regular functions, this ring of regular functions on Z, are nothing else than restrictions of polynomials on the Z.
By C of Cn using polynomials in there.
Yes, yeah, I mean, okay, I mean, let's put x1 to xn. I mean, I don't want to, don't want to write a lot of notation, but okay, this was a little bit confusing. So we need one more notion, but basically this ring R of Z, I mean, this is the point of view we want to consider, that R of Z, in some sense, and we can make it explicit, carries information about this affine algebraic variety Z. But we want to also include some local information, so we are going to define actually a sheaf of functions on my Z. And how do we do this? We define regular functions, I mean, on some open set in Z as a function which around, so this is my Z, which can, and I take a point around a point there exists a neighborhood, and in this neighborhood you can write our function as a quotient of two regular functions. And in this case, you get so-called, by gluing this information, you get so-called structure sheaf. OZ of Z. And basically in algebraic geometry, you study this space X with Zariski, Z with Zariski topology, which is this structure sheaf of functions which are regular on open sets, which is this O of Z.
What's really the localization?
Yeah. I mean, I am you do this by localizing, and there is whole machinery involved in this, but I just want to explain, remind you, I'm skipping millions of details of the whole construction to give you some idea how we want to generalize this. Okay, so then another thing which we can do, these are affine varieties. Affine varieties are constructed explicitly as these closed sets on which we define the structure sheaf of regular functions. If I want to get an arbitrary algebraic manifold, I take a topological space with a finite cover where each of these pieces is an affine variety, and my structure sheaf on a whole thing is obtained by gluing together these structure sheaves on all these pieces. And now, so we also define morphisms as, so if I have two such varieties and a morphism from, say, Z1 to Z2 we can, for affine varieties, we can embed Z1 and Z2 in some Cn and Cn, and morphism is given by polynomial maps. And then again, we glue these informations together to get morphisms for arbitrary arbitrary complex varieties. So what I want to stress is just this word you just mentioned, and this is localization. That the method you use in algebraic geometry, that you want to study local properties of, okay, geometers care about basic properties of your algebraic variety, and they are reflected in the properties of this ring R of Z. We are interested in representations of some rings. So enveloping algebra and related rings. So therefore, we are interested in considering modules over certain ring. And the idea is, if we can find a geometric model for this ring, then maybe instead of studying modules, we can study some geometric gadgets related to the modules which live on these geometric objects. So let me explain how, in a few lines, how this is done in algebraic geometry. So let's assume that I'm, say, doing commutative algebra, and I want to study the category of modules over ring R of Z. So what is R of Z? R of Z is the ring of regular functions of this structure sheaf. Of global sections of the structure sheaf. If the structure sheaf, let me remind you, for any open set in Z, we attach regular functions on this open set R of U. So if I take whole Z, I get my R of Z, which is also denoted as global sections of our structure sheaf R of Z on a full Z. So if I have a module over R of Z, what can I do with this module? Let's pick a module, say M, and I can look at the structure sheaf, and if I have this structure sheaf is what? This is collection of rings attached to open sets with the restriction operation. If I have a regular function on a bigger open set, I can restrict it to the smaller open set. In particular, if I have globally regular functions on whole Z, I can restrict them to an open set. So therefore, my O of Z is a module over global regular functions R of Z. So I can form this tensor product. And this tensor product is a sheaf of modules because on any open set, I have this tensor product on which regular functions on this open set act. I mean, does this look familiar or plausible? I'm skipping a lot of details, but I mean, this is, what is important is to get the flavor of this construction so that we can generalize it. And definitely in these lectures, we are going just to scratch the surface of this subject. But what I want you to get is some information of what is actually going on. So basically, in this way, we constructed a functor from modules over R of Z into modules over, so these are over O of Z. So these are so-called sheaves of O of Z modules. And what are these sheaves of O of Z modules? For any open set U in Z, we attach to it, say, M of U is a module for O of U for regular functions on this open set U. So therefore, this assignment in particular gives us something for the open set U, which is equal to Z. So this is this M of Z, which is so-called global sections, again, of the sheaf M. I mean, what is this sheaf of modules? For any open set, I have a module over regular functions on this open set. If I take open set to be everything, I'm just getting global sections of my module. Yeah, so this is basically just the definitions of these gadgets. So this tells me, and what is this thing? This thing is a module over global regular functions on Z. So, they are nothing else than this R of Z, because this is how our sheaf is constructed. So the functor of global sections, gamma of Z blank, goes from sheaves into modules. Of course, if you really studied algebraic geometry and if you are careful about this, then there are some technical things you observe here. So, of course, I didn't make any statement, but let me now make the fundamental statement which we want to modify. So this is a theorem of Serre's. Which says the following. So let Z be an affine variety. Then the functor, Yeah, okay. So this functor is called localization. What we already heard this term because it's obtained by localization procedure, and this is the functor of global sections. Excuse me? Okay. Let me just finish this and then write down the statement, and then I will explain this precisely. I mean, I assume the familiarity with sheaves, but I can go through the definition of this. So then the functor, say localization functor, is an equivalence of the category MRZ with the category, and now I will put here QC, which stands for quasi-coherent, and I have to explain this to you, OZ, and its, say, inverse, it's actually quasi-inverse, is the functor of global sections. So before I answer your question, let me, I mean, even if you are not familiar with all the details, this theorem, let me point out what is the idea here. You have a category of algebraic objects, a category of modules over a fixed ring. This category is equivalent to another category, which is more complicated at the first glance. But actually, the gadgets, which I will discuss at the moment to answer his questions, are of local nature. They make sense on small open sets. So therefore, we can hope that we can cut the study of objects here to studying some local properties and then going from local properties to global properties. So this, I'm using this more as a philosophical statement than a mathematical statement. But this is the motivation for the applications of D modules in representation theory. Yeah. No. Here I have to get the theorem. Here I have this functor, and I have the functor going back, but they are not equivalences if I don't assume quasi-coherence. So, but I will give the definition of quasi-coherent in a moment, which is not particularly important, but it just makes the statement correct. It's important when you calculate something, but at the moment we are just doing Friday afternoon discussions. So, okay, let me answer his question about modules. So I didn't define sheaves precisely. So what is a sheaf of modules? I am taking open sets in my Z. And to each open set, I attach M of U, which is a module over O of U. But this assignment has certain properties. For example, if this is my O and this is my V, then I have, of course, V sits inside U, so there will be a restriction map from M of u into M of v. Of course, for functions, we have the obvious restriction map. You take a function, restrict it to a smaller set, so you know what O of u is, and you want that this arrow is a morphism of corresponding modules. But there is another property which is important, and this is called, I mean, such a gadget is called a pre-sheaf, but I want more. I want the following. Let's assume that I have an open set, and it's covered with a bunch of smaller open sets. So I want to have certain locality property. If I have, so this is my big U, and I'm restricting them to the elements of the cover, UI. So this is my restriction from U to UI. So let's assume that here I have M and M prime such that restrictions from U to UI of M are the same as the restrictions from M and UI of this M prime. So I have something living on U, which I restrict to the pieces in the cover, and in each restriction I have equality. I want that this equality implies then M is equal to M prime. So I can detect equality by looking at local information. This is one thing which enters the definition of a sheaf. Of course, for functions, this is obvious, because functions are defined by values at points. So the other thing is that I can glue sections. So let's assume, let me do something simpler. I have, say, 3 pieces, and I have sections M1, M2, and M3 such that when I restrict M1 to say U1, I will also use this notation for restriction, just as for function, to U1, U2, that this is equal to the restriction of M2 to U1, U2, and say restriction of M1 to U1, U3 is the same as M3, U1 intersected with U3. So I am having these 3 pieces. On each intersection, these restrictions agree. Then the statement is that I can glue these sections and construct a section M of the big M of U such that M restricted to UI is MI. Yes?
Could you recall the definition of a section of a sheaf?
By section, I mean an element of this guy. I mean, sorry, I'm. So basically, sheaves are collections of data attached to open sets, on which you have a notion of restriction, which the equality can be detected locally, and you can glue local things to build things on bigger open sets. I mean, does this?
Well, actually, my question was, so I know what a sheaf is. I was just wondering how you build a module over top of a sheaf.
But this is just that on every open set, you have a module structure which is compatible with all the restriction maps.
Okay, it's a module over the ring that you get
Yeah.
associated with that open set.
I mean, this is O of U is sheaf of rings. Regular functions as sheaf of rings. So in each open set, you will have a module on the regular functions on this thing. Okay. Okay, I mean, we spend more time discussing this, there's no problem. Okay, so some people ask what this means. I mean, this is really not a big thing. Quasi-coherent means the following, that locally your sheaf is very simple. So if I take a point and then there exists a neighborhood U such that, say, my sheaf M, let's see, okay, let me go, M restricted to U. I mean, I can always restrict a sheaf. I take a sheaf and I just take open sets sitting inside a given open set. This will define me a sheaf on that open set. So I restrict my M in U, and I want that this is a very simple gadget. So this is a co-kernel of a bunch of copies, which can be infinite, of OU by a map from another, say, OJ. So I have these are sheaves of regular functions. I take the sums, which can be infinite. I look at the map from one into the other, and I want that this thing locally is just co-kernel of this map. You can ask, why is this condition needed if you don't have, this corresponds, this is the localized version of an obvious fact that when I'm dealing with a module, I can take a bunch of generators, and then my module is a co-kernel of a free module. And if I don't assume something like this, then basically I get sheaves which are so complicated that I cannot calculate anything with them. I don't know where to start. So this is some kind of local property I need to study this problem. So now, when did I start?
10 minutes.
Well,
Exactly 50 minutes ago.
okay, yeah, this is what I thought.
Well, actually, maybe 49.
Okay, that's good. This is exactly what I need. So, what we want to do? What is the, say, philosophical message of Serre's theorem? That if you want to study one category, you can try to convert, by this equivalence, your problem to equivalent problem in the other category and study it over there, or vice versa. So, I mean, in algebraic geometry, you usually are interested in Z, but this ring is very complicated. So what do? You actually study local properties of Z by studying these modules over this sheaf, and actually say they are stalks, for example, which is a problem in commutative algebra near the points of Z. So basically you study local property of objects in here and then try to draw some conclusions about objects here using this information. So what we are going to try to do for representation theory, we cannot start immediately with Harish-Chandra modules because they are just too complicated. We don't know exactly where to start. But let's look at the enveloping algebra. See, enveloping algebra is something quite complicated. And we would like to have a geometric model of the enveloping algebra which allows us to do something similar as over there. One cannot do this exactly with enveloping algebra. There are problems. So we have to do, we have to quotient out something. And in this last few minutes, let me try to formulate at least the idea of the construction. So, and then next time we are going to discuss this in more details. So remember, in the enveloping algebra, we have our center of the enveloping algebra. And this center is a commutative algebra. And what we can look at the center are its maximal ideals. So let me take a maximal ideal in the center. Let's call it I. And this maximal ideal, because we are working, or see, I mean, this is z of g modulo this maximal ideal are just complex numbers. Now I can look at the ideal generated by u of g. This maximal ideal, because it's in the center, generates a two-sided ideal in the enveloping algebra u of g. So I have a quotient of the enveloping algebra by a maximal ideal in the center. You can argue, and let me denote this for the moment by ui. This quotient depends on the choice of this maximal ideal. And you can think that this is a strange construction, but let me point out what Peter mentioned in his lectures. If I have, if V is an irreducible module over u of g, then Peter said that it has infinitesimal character, chi v, from z of g into complex numbers, such that chi v, that z acts on our module v by multiplication by chi vz. So this means that the kernel of chi v is a maximal ideal in z of g. So if I look at an irreducible module, this irreducible module is in a category of modules over ui for some I, and this I is just the kernel of the infinitesimal character. So replacing the enveloping algebra with a collection of such algebras is not so bad. And those algebras have simple geometric models. So let me explain what I mean by this. So let's assume now, I can do this in more general situation, but let's look at SL2C. In a first lecture, Castleman discussed the action of the group G's SL2C on projective space, P1. So P1 is so-called flag variety of SL2C. I can look at this action of the group on P1. I can differentiate this. This is a regular action in sense of algebraic geometry. I can differentiate it, and what do I get? I get the mapping of G, of the Lie algebra of G, into tangent vectors, vector fields on pi 1. When I can replace G by the enveloping algebra. Remember, you get enveloping algebra by making monomials in elements of Lie algebra and spanning an associative algebra over this. So what happens here if I just act by products of tangent vector fields in their linear combinations? What kind of action on P1 I get? I mean, what are the objects I get here? Differential operators, yes. So I'm going to differential operators on P1. And this is one of my models. If I take here the maximal ideal in the center, which corresponds to trivial representation. So to the infinitesimal character of trivial representation, let me denote this guy by I0. Then this...
The ideal that comes from the kernel of your infinitesimal here.
Yes, yes. So here then I have U of G divided by I naught. So this is the maximal ideal corresponding to trivial representation. And I have this. And this is an isomorphism. This tells us that if I take the quotient of the enveloping algebra of SL2C, quotiented out by a by the ideal generated by maximal ideal in the center, which correspond to trivial representation, I will get that this algebraic object corresponds to geometric objects consisting of all differential operators on a Riemann sphere. I can replace this I by I naught by arbitrary I, but I have to do something here. Instead of differential operators, I have to consider so-called twisted differential operators. But at the moment, I don't want to say anything about this. But let me now explain what the game is. This is what Rishi actually pointed out. This is how I got these formulas at the beginning of the lecture. I mean, I have Riemann sphere. I took these guys. I took a chart. I took a copy of C, which was a chart of P1, and I wrote down the action of differential operators explicitly. But what we are going to do with this, instead of looking at these are global differential operators. Instead of this, I can look at a sheaf of differential operators. I mean, I will discuss this next time. I mean, now, take this very naively on each open set. I can look at differential operators which act on functions there locally. And then I can play the localization game. So what can I do? I can look at the category of modules over this quotient of the enveloping algebra by the maximal idea, by the ideal generated by I naught. I'm sorry, here I lost U of G. Because, I mean, this. So I go from here into sheaves. Again, they are quasi-coherent, but you can forget this. Over differential operators on P1. And this functor is the localization. And it's how it's defined. I take this sheaf of differential operators. The global differential operators correspond to this quotient of the enveloping algebra. So, and these are modules over this, so I definitely can make this tensor product. And I can go back by the functor of global sections on P1. So now the miracle happens. Because, you see, anybody who really spent some time learning algebraic geometry knows that there is something extremely fishy here. In Serre's theorem, this is an affine variety. Here, this is a projective space, which is just on the opposite end. But the miracle happens here that the Serre's theorem holds exactly in the same fashion in this situation. So these two arrows are equivalences of categories. So what does this mean? This means that all of our modules, all the modules we studied and we calculated are nothing else than global sections of some sheaves. And we can understand, I'll try to understand these sheaves here and then calculate their global sections and get some insight about representation theory by studying these sheaves of D modules, which are just sheaves over rings of differential operators. What is the advantage? The advantage is the differential operators locally are very simple. Especially in this case, they are differentiations times some regular functions. Enveloping algebra is more complicated. So, I mean, this is the message I wanted to convey in a very vague form. And then next week, I will try to explain how we can get some modules, all modules actually we mentioned from this geometric point of view. There will be one surprising benefit, and this will be that it's very simple to classify objects here, irreducible objects here, because you will see the reason for this. I mean, it's very easy to understand them. And this equivalence of category tells us irreducibles go to irreducible. So it will give us another way to classify irreducible objects here. For example, we will be able to see in this picture geometric interpretation and homology. And all these results, we struggled using differential equations, and these things can be seen from this picture. I mean, depending on your taste. If you are an algebraic geometer, they will be much simpler than using differential equations. If you are not, maybe it will be much worse. So, but basically, this is, in very naive and rough words, the idea of the subject and the idea of the attack of the problem of studying representations using D modules. Any questions? Yeah. Where? Here? No. This is a very good question, because this would make the problem more complicated. What happens here that you get all differential operators. So if you cut out a small piece of your projective space, in your sheaf, there are all differential operators. I mean, the structure coming from G is gone. And this is like in algebraic geometry. Locally, you have your local ring of algebraic variety if the point is what happens further out. And the same situation happens here. No, these are just all differential operators on P1. Any other questions? Yes? Yes. And the only reason for that is for simplicity, because I wanted to have here genuine global differential operators. Otherwise, I will have to construct something fancier. These are twisted sheaves of differential operators, which basically you take on each set, open set, take differential operators, but then glue them in a weird fashion together. I will write you the formula, I think, in one of the lectures next week, just so that you can see how it works. In a P1, this is not so bad because, again, let me use picture Bill was showing. I have these two copies of C, which are tangent planes to Riemann sphere. So I will take differential operators on this and differential operators on that, but I will, on a C star, I will kind of twist them when I glue them together. And then, depending on this twist, I will pick up whole family of maximal ideal in the center, and I will be able to do this construction for arbitrary infinitesimal character. This looks like a serious complication, but let me point out that to study locally the problems of modules, so locally these are ordinary differential operators. So local property won't depend on the twist, just how you put them together. This is, if you look at the formulas for Verma modules, all Verma modules look the same, that you have all these weights, and you have up and down operators, just the numbers are different. And the numbers are different because these twists are different. I mean, this is at least the module way of looking at this. Any other questions? Okay, if not, then I'll finish for today, and then tomorrow, if anybody who has any questions about sheaf theory, algebraic geometry, and these nonsensical things, we can discuss this tomorrow.